Welcome, everyone, to another episode of the Manufacturing Matters podcast, where we talk about how automation trends and technologies are shaping industry, logistics, and other sectors of the global economy. I'm Dan McCarthy of Tech B2B Marketing, and joining me today are my colleague, John Lewis. Say hi, John.
Hi, Dan.
Hey. And Patrick
How's it going, everyone?
Sorry. Also joining us is Patrick McFadden, CEO and co-founder of Iris Dynamics. Welcome to the podcast, Patrick. Thanks for joining us today.
Absolutely. Thanks, Dan and John. Great to meet you, and thank you for having me.
Yeah, it's our pleasure.
To be here.
So, Patrick, let's kick off by having you tell us a little bit more about Iris Dynamics. And you're the co-founder, so a little bit about why and how you started it, and what prompted that, and where you are in the market today.
No, I'm one of the co-founders, and we started the company quite a while ago, actually. At this point, oddly enough, not from the manufacturing background initially. We came out of the aerospace sector, specifically building components for force feedback or control loading for like commercial simulation devices. And that's sort of where the core technology was developed, and then over many years it sort of got dragged kicking and streaming into the robotics sector, and now into the automation sector, and it's sort of where we are now.
And we were talking a little bit before we kicked off here that because your first product was a flight control simulator yoke.
Yeah. So we were basically a subcomponent in commercial simulation systems. Force feedback is probably the term most people are familiar with, but essentially it's a back drivable motor. So you apply a certain force command to it; it'll output that regardless of it's being back driven or not. And the important piece there is, at least in an aviation application, the amount of pressure that a pilot feels on their fingertips on a yoke or a flight stick or a cyclic or whatever conveys very important information. And in a simulation environment, you need to be able to convey that information back to the pilot.
Right.
That's where the core piece of technology came out of.
That's right, and everything's evolved from there, from your motion control. Right.
That's correct. Yeah.
Okay. In Patrick, in manufacturing, in terms of an existing labor shortage and increased use of automation, can you talk about some applications of direct linear drive technology for automating routine tasks, and what the benefits are compared, to using traditional drive systems?
Yeah, absolutely. And I mean, it's an interesting question because it's somewhat diverse list of benefits. I guess one of the things to sort of drill home with smart devices, which is sort of one of the places that one of the ways we're basically describing this kind of device. They're fully integrated, at least in our perspective. They're fully integrated devices. That means like the motor driver itself, the stators, the motor controller, all the position sensing, and in our case force sensing, is all fully baked into the motor. It's one device, so you don't need to have quite as many cables going back to the cabinet on the other side of the room. Because of that, they're much faster and easier to install. You don't need to have nearly the same amount of engineering time spent to get these things up and running. Because you have this fully integrated device, and you have a lot of logic processing on board, you have the ability to measure and report force. You can use these devices in applications that, frankly, you really couldn't use before. So some of the tasks that we're finding right now in the manufacturing space, a lot of assembly tasks, so things like press fitting inserts and needing to make sure that you have the right distance as well as the right amount of force being applied during that process. And if you exceed some force threshold or some position number isn't met, it can throw an alarm. Applications like driving and hammering rivets or other sorts of things like that. Lots of applications where you might want to maintain a constant amount of pressure to something, and again, because it's a compliant motor, back drivable motor. So things like rolling mills and that kind of thing. You have like a drag knife, or you've got like a sensor that you need to have being constantly pressed against something, and maybe the thickness of the material is varying. Lots of applications where you're synchronizing movement. Honestly, in the manufacturing space, if you wanted to have an application where you have some amount of force control, the most practical way to do that right now is basically with pneumatics. You can adjust the amount of pressure in your system, and that's how you can make them work, and that works great to a point. But as the seals wear out, as they get stiff, your calibration gets to go out of whack eventually. And if you've got an application where you might have to have, a number of motors firing synchronized, but with a certain amount of force, that can be a problem. And so we're finding a lot of applications in those sorts of spaces too. Fixturing, work holding, that type of thing.
Yeah, just a quick follow-up on that. You talked about, a little bit about making these systems smart and how that expands or influences how the motors are applied. Can you talk about how smart should these motors be?
Yeah, that's a good question. Yeah. So I mean, again, as I mentioned, smart motor in our definition here is, again, fully integrated. So you've got all the electronics that are needed to make it work, living directly on the motor. So you're not going off and buying separate motor drivers. You're not buying separate VFD. You're not necessarily buying a separate motor or a separate control device, as well as obviously all the sensors and all that are all fully integrated. And the advantages of doing that, obviously all the integration stuff we sort of touched on already. Less cabling, easier setup. You don't have to mess around as much with calibrating everything because it's already pre-done. But the other side of this equation is by moving the motor control, like specifically all the control loops, like the PIDs and all that, locally to the motor, you can now have the motor do some kind of interesting things. Much faster response time, so much lower latency. But for example, if you wanted to measure changes in mechanical backlash, you could do that because, again, you've got force data as well as position data, all being processed locally very, very quickly on the motor. Yeah, I mean, you can get into a lot of discussions about that. How smart it should be is a good question. One of the things that we found specifically with our customers in the robotic space is because we've been able to move so much of that overhead equipment, which is also a point on footprint, but move that into the motor itself, you can offload a lot of the processing power that the main control device was having to do before. So now at this point, the motor the robot's controller can say, okay, hey, I need you to perform an action. And then how that action gets performed can be dealt with directly on the motor itself.
So that involves logic, obviously.
Yeah.
Is the logic a component that you also provide, or do you provide the software? How does that? Where the control?
Yeah, for sure. So it's all built into the motor itself. So it's built into the motor's firmware,
Okay.
and there's a lot of different ways you can control it. One of the interesting things we found at our last Automate show actually was a lot of people wanted the functionality of these higher level controls that I'm going to talk about in a minute, but they didn't necessarily want to have to get deep into the weeds of integrating it and programming it. Right. And a lot of these folks now are just using very simple digital or analog triggers to then have the motor itself do some really complicated things, which means they don't have to write a line of code, but they can still get the functionality I'm going to talk about. So again, having this integrated force control feature, again, without the need for external load cells or external encoders, and some interesting black box stuff on how we're pulling that off. You can have a number of different control modes operating locally, fully on board the motor. So things like force mode, so it outputs a constant force. Tell it to output X number of newtons, and it'll do that regardless if it's being back driven forward or backwards. So applications like polishing and grinding, as I was mentioning, like drag knives, rolling mills, that sort of application. Position mode. Something everyone's going to be familiar with. Obviously, go to position A, go to position B. Straightforward. Obviously, we can do that. Kinematics mode, which is the interesting one that we've been finding a lot of customers using. So again, you can basically pre-program set profiles that you want the motor to do, and those can then be triggered from like a simple digital signal, right? So for example, if you're doing like a replacement of a pneumatic system, you can tell the motor, hey, I want you to do this motion profile just by plugging it into a laptop, a little simple free GUI that we have. You can program it. You don't have to write any code, hit save. And every time this digital line gets pulled high or low, it'll do the thing. And then in this particular case, the cool thing with that is you can then wire that into the exact same solenoid control signal that you were previously using in your pneumatic system.
Okay.
But now this is going to be constantly performing the correct movement all the time, every time. And then the other one, which is kind of interesting, would be what we're referring to as a haptics mode, where basically the motor acts as a programmable spring or programmable damper. It can simulate inertia, it can simulate mass, vibrations, whatever, and it can do these modes sort of stacked on top of each other. So those are sort of the functionalities that you can do with these devices.
Just another quick follow-up, sorry, John, but I'm curious. So
Yeah, no
a
worries.
lot of what we talk about is machine learning a possible addition to this technology that you could
Yeah,
developing?
it's a great question. Obviously, that comes up a fair bit in our conversations with people. So, I mean, robots are obviously blind, unless you add vision to them, and robots can't feel unless you add more sensors to them.
That's right.
And of course, you can do all those things, but they cost time, they cost money. You got to have cables, you got to have sensor amplifiers and image processors and all that nonsense.
Right.
So, and if you need that, absolutely go off and do it. The advantage of using a smart motor or smart device like what we're offering, at least in the linear space, it allows you to have a lot more functionality without the need to have all of those additional sensors and all that additional overhead, both from install and from mechanical stuff. And for example, let's say you had a pneumatic a line where it has a bunch of pneumatic motors doing things, and you wanted to throw some fancy machine learning at that, or you wanted to do like predictive maintenance or something like that.
Right.
Well, you probably don't have position data on those motors. Probably only have a rough idea what the force data is. You probably have like the PSI of the system.
Sure.
You definitely don't have a load cell on the end of every single pneumatic piston. And the advantage of using this sort of approach into an application like that is now all of a sudden, hey, you've got a ton of data available. Now the motors can deal with a bunch of that internally themselves, so they can make sure they're adjusting and increasing or decreasing force to hit whatever it is that you need to do. So you can get better line speed, you can get better repeatability, all that jazz. But at the same point, if you are looking at integrating some of these higher level things into say AI and machine learning and all that, the data is now available for you. So we aren't looking at implementing AI systems or machine learning ourselves. We're enabling it. That's the whole point. Yeah. And also like that's just comes with the beast of what we're providing. The data's there. You can use it if you want to. You don't have to. But it's there should you decide you want to use it.
Very cool.
Hey, Patrick, you talked a little bit a few times now about replacing pneumatic technology. I see pneumatics is often used in advanced robotics, and I'm wondering if and how is smart linear drive technology being used in advanced robotics? Like to provide high precision motion control, maybe in the end of arm tooling, maybe working with cobots or autonomous robots, for doing different tasks like assembly, packaging, or machine tending.
Yeah, absolutely. No. Again, great questions. So a lot of applications, obviously, you might want to have some sort of force sensing, force control, specifically in cobot applications and end of arm tooling. And a few ways you can do it. It's usually done as I mentioned with a load cell or some sort of force sensor. And of course, in those applications, it's usually like the robot goes to a position and do not exceed a force, right? So it's not necessarily back drivable, not necessarily compliant. There are ways of doing that, but complicated and expensive, and somewhat rare, to be honest, in manufacturing environments. Pneumatics, obviously, easier to install, easier to use, but there's problems. You don't have data, and they have to basically be serviced on a somewhat regular basis if you need to have good repeatability on that force control. And we'll gloss over issues like cost and power consumption and replacing compressors and air dryers and all that. Going to a smart linear motor or integrated linear motor, because it's fully integrated, means it's a much smaller footprint. Also, our devices are all low voltage DC, which makes them very well suited for mobile applications. So things that are running off of battery, or maybe it's an alternator system. We've got lots of applications that are vehicle mounted, more onto like semi-autonomous driving systems and that kind of stuff. But obviously, there's other applications in the manufacturing space. By having by having that force control functionality and that backdrive ability, as well as tons of data that can be streamed very rapidly, that unlocks a lot of very, very cool applications in those spaces, which I unfortunately can't really talk too much about.
Right.
But yeah, I mean, I think long term, obviously, we all know this is where things are going. Things that I can talk about, definitely end of arm tooling, as I mentioned, polishing and grinding applications, that would be a good example of that. And also by virtue of having to, or being able to eliminate, all those external sensors and the encoders and the load cells, because, these are fully encapsulated, IP68 devices, all fully potted. We're calling them a solid state motor, essentially. It's a single moving part. They're significantly more robust, specifically, talking about load cells. They're kind of fragile little things. You hit them the wrong way, they're cooked. So that allows them to be used in, somewhat harsher environments. And by virtue of the fact that, they can be set to be a compliant device, locally on the motor, that basically means that even if you had like a, sort of a lower tech sort of system, you could use one of these devices, set it to say, hey, when X and Y and Z analog or digital signals are set to whatever, go to this force output and just hold it. And so that's really useful for people who are, like, say, in the OEM space, looking at doing upgrades and modifications to their existing systems without wanting to get really, really deep in the weeds with huge amounts of redesign. So I don't know if that answers your question or not, but that's some of the spaces that we're seeing there.
Great. Hey, you mentioned compliance, being a compliant device a couple times, and I have to be honest, I'm not that familiar with what that term means. Would you mind clarifying for me?
Yeah, absolutely. So, so normally if you think about like a robot, it goes to a position and it holds it, right? Goes to a position and it holds it, typically position control. And if you go to grab onto the end of that arm and you try to move it back and forth, it's, in most cases, it's not moving, which in a lot of applications is exactly what you want. Nice, stiff, rigid. For certain applications, that's absolutely the right thing. But us being a compliant motor, we command a force. So you tell the motor, well, let me rephrase it. You tell the motor you want it to do, it ultimately internally is commanding a force. And with that, if you overload it, and it's not to exceed some amount of force, it will now comply. It will backdraft. Very smooth, so no torque ripple, no cogging, no detents or anything like that. Just it feels honestly like something that's organic, or like a spring. And that's basically what we mean by compliance here. So typically a robot, you're going to say you've got like a robot arm or like some other sort of more complex robotic system. They're typically position controlled. So the kinematics model says go to position A, go to position B, go to position C. Maybe you've got sensors, so if it detects an obstacle or some force spikes beyond some limit, it'll stop and throw a warning light. The advantage of using force-controlled motors is essentially the robot can be told to output an amount of force until a position is reached. And that's actually how us organics work, right? When you're moving your arm, you're not moving it to a position per se. You're applying a certain amount of force to your muscle until you get to a position. And so it's getting a little bit into the weeds on the technical stuff, but that's basically the sort of functionality that our type of technology unlocks, and smart devices, smart motors ultimately unlock.
That's very cool.
Robotics applications. And that's where we think it's ultimately going to go.
I appreciate the clarification, Patrick.
Yeah.
I'm wondering how do you see smart linear drive technology such as yours contributing to efficiency and sustainable goals at manufacturers?
Yeah, for sure. Probably the lowest hanging fruit on that. Not to hammer on it too hard, because it's not the only thing that's out there. But pneumatics is a big one. The amount of electricity costs in running pneumatic systems is non-trivial. They are not very efficient. To say nothing of the overhead costs with replacing the equipment and the compressors and all that. So that's definitely the biggest piece that we see, and we're definitely not the only people playing in that space looking at electrification. Obviously, with having data available, that can increase or that can decrease spillage. You can have tighter controls on your line, better repeatability. Having integrated position and force right there at the end of the robot arm, or even if it's just a machine that's knocking something off of a line or something, having that data right there can allow you to implement like quality checks in the manufacturing process that you wouldn't typically do. For example, there's an application that I know that we've had where you're knocking something and it can detect the mass of the thing that it's hitting because it knows knows what the joules are when it hits it and how it accelerates or decelerates, and those are the sorts of things that pretty tricky to implement using more traditional approaches, that helps with things as well as typically faster line speed too. So you can move these motors a lot faster than a lot of other systems.
Patrick, a lot of what you talked about is robotics, and the integration of this technology obviously gives it some unique capabilities. Is your robotics really seeing most of the applications within industry in manufacturing, or talk to us? I'm dying to ask you about examples of into the details. But I love those big stroke trends of where this technology.
For sure. Yeah, no, and I unfortunately can't really get into a lot of the nitty gritty because a lot of these things we're a subcomponent that often ends up in a subcomponent of some other system, and there's a few steps before it actually gets to the shop floor. We think that there's going to be a paradigm shift to having fully integrated systems. Smaller, more compact, more efficient, easier to install. I mean, cheaper. When you get onto that one, it's big cost reductions.
Is this within robotics specifically, or are we talking larger, like
all applications?
Conveyors? Okay.
Yeah, all applications. Especially when you start talking about anyway, cheaper. That's a fast way to describe it.
Okay.
Force is also typically an afterthought in most applications, mainly because traditionally it's either been not great or has been ridiculously expensive. So you'd never really see it being used unless you really, really needed it.
Okay.
That being said, if you can drive the cost of all these systems down low enough to the point that we think it's at now you're giving the engineers and machine builders and the designers and even like the techs on the floor the tools to now enable force control, force sensing, and that allows our customers to do some very, very interesting things.
And am I extrapolating here? But would that be greater cost efficiency? Is that the line you're drawing here? Is that force previously was not a huge deal until it now has an ability to?
Again, we come out, as I mentioned, at the beginning here. We came out of an aerospace background,
right?
And let's say you wanted to have a compliant back drivable motor in that space. For simulation is a good example. You could easily drop $10,000-$20,000 on a single axis. You could go a lot higher than that if you wanted to. So you're not going to put you're not going to put $520,000 little actuators in your machine if you're an OEM typically.
Right.
But if that $20,000 device now can be installed for like $1,500, that's
sure. Okay.
We're getting into different levels of number here. And again, because it's fully integrated, it's got all the logic and processing directly on the motor. And absolutely, you want to get deep in the weeds on the programming, you absolutely can. But if you don't want to, and this is actually another interesting thing that we're seeing, a lot of customers who are, in environments, they're in manufacturing, but, they're probably a smaller company. They don't necessarily have, like a big IT team. They probably have engineers, but they're probably mechanical. They probably don't have much, if any, computer programming or software stuff. Some of these guys don't even have PLCs in their facilities. And by having a device like ours, where all that technology and the intelligence and that software controllability is built into the motor, and they can access that through a laptop with free software, and they just point and click and drag a thing around. That allows guys on the floor to be implementing some different sort of functionality that, again, you would never do if you're having to do a custom built $20,000 axis for one device.
Right.
Yeah.
So this paradigm shift you're discussing, you're telling us about, is this based on the customer trends you're seeing, the customer requests you're seeing?
Yeah, absolutely.
Is it all going one direction? Okay.
Yeah, absolutely. And I mean, and we're actually seeing a bit of a split too. So like you've got the robotics guys that are obviously going way up with what they're doing with it.
Right.
But again, they're also being able to offload a lot of their processing, to our motor, right? Because again, they don't need to deal with the loops and all that. They can just tell it to do the thing, and they can communicate using whatever fancy APIs you want. But at the same point, you've got folks who are looking at implementing automation, into applications like a small like cookie manufacturer, right? Is an example. Like, these are not guys that are going to be buying a cobot or implementing fancy control systems or implementing vision or anything like that. But yeah, a couple $1,000 for a motor that they can pre-program to do a thing whenever like a digital trigger is set. That's a different level of enabling what the customer can do.
Sure.
Yeah.
And actually, speaking of customers, is this largely being driven by the adoption? Is it largely being driven by OEMs who are trying to simplify their process? I can see an advantage here to deployment as well. This is going to simplify deployment if you can.
Yeah, absolutely. So our primary drive is OEM. That's where our primary push is. But also integrators as well. Yeah. So those are sort of our two main drivers. So direct sales to OEM is definitely where most of our business is, and then integrators as well, because of how it eases adoption. And I guess we also have a lot of people using them in like test and measurement applications. So a lot of people are using them for product testing, line testing. Some laboratory stuff, some sort of more aggressive sorts of things, product accelerated life testing, that kind of thing. Because some of the functionality that we've enabled for our customers in the robotics side is you can just plug this into USB into a computer running MATLAB or LabVIEW, and there's a bunch of libraries, and they can be immediately using LabVIEW and doing science with this thing like within it's gonna be 20 minutes of unpacking it basically.
That's very cool.
Yeah, which you're not doing that if you have to wire up your
your
motor drivers and controllers, and I need fixturing for my position sensor, and amplifiers for my load cell.
You went to science, yeah.
So.
Yeah, I had a question, Patrick, about how these things are connected up. With everything integrated, I'd like to know a little bit about how you actually wire them in, hook them up. Can they be linked in series and parallel? Can they be set up as a leader and a follower to communicate with each other?
Yep, all of the above. Yeah, absolutely.
Okay.
And they can be done in multiple ways too. Again, sort of the lowest common denominator, the easiest, lowest tech way of doing it is we've got like a little breakout board that you can plug the motor directly into, and it's got a pile of digital and analog I's and O's. And then using a little GUI, you can configure it to do whatever. You want it to go to a position, you want to have it output a force, you want it to feed force data out on an analog channel, you want to feed position data out on an analog channel, you can do all that. That's the easiest way to do it. Next step up, basically you can plug it directly into a PLC, and then we've got a bunch of libraries so you can get the PLC to do whatever it is that you want it to do. And again, the full set of functionality is available there. And then for folks that are mostly more on like the robotic stuff, like they're doing autonomous vehicles or ship-mounted equipment, that kind of thing. They're typically talking directly to the motors over a serial link, and they can set their streaming data as fast as they want, and running these things on FPGAs for fancy kinematics applications. So you can get as simple as you want or as complicated as you want, basically.
Cool. And we mentioned pneumatics a couple times and replacing pneumatics, and I'm just curious if these have enough force to replace like other fluid power systems like that might use hydraulics in certain applications.
Yeah, in some applications, yes, but definitely, we're not looking at putting these on like a big excavator or anything like that anytime soon. Yeah, so they're our currently our largest motor outputs 200 and something pounds. 1,000 newtons or something like that, whatever that is. So that's sort of the force range. So in the realm of pneumatics is sort of where we're at, and of course smaller devices are another piece of it too. So
Great.
Yeah.
This is a lot to think about. Is there anything we haven't asked that you feel it's
Yeah. Well, I mean, our feeling here is, we think this is where everything's eventually going to go. Not just linear motors, but rotary motors and all the rest of it. Moving the motor driver and the sensing and some level of the control directly onto the motor itself makes a lot of sense in our mind.
It does.
You've got everything on one PCB. You don't have a ton of cables going back to a control cabinet. You give it power, give it some sort of signal, if you need it. In some cases, you don't even need a signal, you can unlock a lot of functionality. You can reduce a lot of footprint, and the big thing that we're also finding is that there's not enough people out there doing this work. There's not enough engineers out there doing this work, not enough technicians out there doing this work, not enough guys on the shop floor. It's hard to find people. Going to a fully integrated solution saves so much time with respect to integration, right? Again, you're not having to run a bunch of extra cables. You're not having to figure out how to program this or that, or like, oh no, the firmware on this motor driver is not the right firmware. It's not going to be compatible with this controller, right? Bug hunting, a disconnected cable for like for an encoder somewhere. It eliminates all that hassle.
Sure.
So it allows you to be up and running really, really fast. Which irrespective of the fact that we're seeing huge cost savings on the equipment itself. Also, the amount of money that you're saving on the amount of time that the customer is needing to spend to get this thing up and running, that's a big saver too. Because if they don't have to spend 3 days messing around getting these things wired up, they can spend those 3 days dealing with their actual problem that they have.
Right.
Not how to make a motor move in and out.
What about maintenance? Is once you the one counter argument I ever hear about integration is maintenance, because you have to dig deeper into a system to find the problem. But is that
absolutely a great question? So from a mechanical maintenance standpoint, again, these sorts of devices that we're talking about, it's direct drive. Basically, it's fully solid state. All the components are fully potted. So there's no gears to wear out. There's no seals to wear out. Occasionally there's some bushings, but they're standard IGUS part, easy to pop out in the field if you need to. And depending what side load you're putting on these things, we're hundreds of millions of cycles on these guys. By being fully potted, fully encapsulated, they're waterproof. They're being used in maritime applications. Very hard to kill. And so, we're seeing, especially compared against pneumatics or some ball screw applications, significantly longer lifespans by a very big margin. So, and of course, the counter argument. Okay, sure. What happens if your motor driver burns up in a traditional system?
Well, at least you've isolated the problem, right?
Yeah, exactly. You've isolated, but with these devices, you've anyway, fully integrated, and modern electronics these days pretty reliable. So
that's fair. Well, Patrick, this has been very illuminating. I find this technology very interesting. I'll be paying close attention to it, see if that paradigm shift comes about. For now, we'd like to thank you for joining us. And Iris Dynamics for giving us a little time to illuminate a little bit more about what your technology is about and where it's headed. If you have any questions for Patrick, or you feel free to send them to us or post them on LinkedIn, and we will get back to you with those answers. If you're interested in past episodes of the Manufacturing Matters podcast, you can find them on our website, manufacturing-matters.com. And for anyone wishing to be in the loop on upcoming conversations about automation, please follow us on LinkedIn. But for today, Patrick, thanks again. John, thank you. And thank the rest of you for joining us.
Thanks so much, everyone. Take care.
Bye now.